So mobility and degrees of freedom both are same. And whenever I say linkage is a mechanism with only lower pairs. Linkage is a mechanism with only lower pairs. It's not possible to have a mechanism with all lower pairs, okay? It's with all lower pairs. We cannot have any mechanism. With all higher pairs, I can say. Let's go through these questions. Try to answer these questions. Yes, what's the answer for this? Footstep bearing is an example of, it's a successfully consistent motion, okay? Footstep bearing is successfully consistent motion. So what's the relationship between higher and lower pairs for planar mechanisms? This is a sliding pair, okay? You can see the animation, this is a sliding pair. And you can see the kind of contact we can have, it's a surface contact, okay? This is a turning pair, okay? This is a turning pair, relative motion is pure turning, okay? A circular rod in a circular rod, this is called as a screw pair. Screw pair is also a lower pair. Screw pair is also a lower pair. And you can see you are having a surface contact. And only 1 degree of freedom it has. This is a spherical pair. It's also a lower pair. But for spatial mechanisms, okay. You can see here there are two different types of cams. The first case you can see this one. This is a force closed pair, okay, sorry. This is a force closed pair, the contact is because of gravity. And this is self closed pair, okay, the second one you can see. This is self closed pair, it can work in any direction, okay. This is self closed pair. In the second case you cannot separate this without destruction of at least one element, okay. So this can be separated only by destruction of at least one element of the pair. So whereas this one, this can be separated. This is force closed pair and this is self closed pair. Okay. So one higher pair is equivalent to how many lower pairs in planar mechanisms? This is strictly valid for planar mechanisms, okay? One higher pair is equivalent to 2 lower pairs. Screw pair is higher pair or lower pair? Screw pair is higher pair or lower pair? Screw pair is a lower pair, okay? Screw pair is a lower pair, and number of independent motions in a screw pair are only 1. Lower pair will have, what is the lower pair? Lower pair will have a surface or area contact, okay? And higher pair will have point or line contact. Point or line contact. And if you see gears, a pair of gears in mesh, you will be having a line contact, okay? For pair of gears in mesh, you will be having line contact. It's a higher pair. Just go through this question. Go through this question. A round bar A passes through the cylindrical hole in B as shown in the given figure. Which one of the following statements is correct in this regard? A circular rod in a circular hole, okay? A circular rod in a circular hole. Third question. Third question, number of independent motions in a screw pair. In a screw pair, number of independent motions are only 1, okay? You cannot rotate the screw without letting it translate, okay? So, if I take circular rod in a circular hole, so these two motions are independent, okay? A circular rod in a circular hole. So I can reciprocate it without rotation. Or I can rotate it without reciprocation. Or if I want to do both, I can do both of them simultaneously. Whereas in a screw pair, so this is not possible, right? Here both are independent. So I can say reciprocation is not getting affected by rotation, or rotation is not affecting reciprocation. This independent, okay? If I just want only reciprocation, I can have it. If I want only rotation, I can have it. Or if I want both of them, I can have it. But in a screw bed, they are dependent, okay? Yes or no? When you rotate the screw has to translate by pitch amount. So, it's a circular rod in a circular hole, okay? A circular rod in a circular hole, which statement is correct? For a circular rod in a circular hole, which statement is correct? The two links shown form a kinematic pair. The pair is completely constrained, the pair is incompletely constrained, the pair is successfully constrained. Which option is correct? A circular rod in a circular hole. A circular rod in a circular hole is incompletely constrained, okay? Incompletely constrained. Is it a kinematic pair? Is it a kinematic pair? It is a kinematic pair, okay? It is a kinematic pair and it's also incompletely constrained kinematic pair. So both the options are correct. Statement A and statement C are correct. Let's try to find degrees of freedom for this question. Number of degrees of freedom of a planar linkage with 8 links and 9 simple Revoute joints. So degrees of freedom, we have this formula. This is 3 into n minus 1 minus 2 times lower minus higher. Okay. So he's saying number of links are 8. Number of links are 8. Number of Revoute joints. Revoute joints in the sense turning pairs. Turning pair is a lower pair, okay. So no higher pairs. Higher pairs are 0. So degrees of freedom is 3 into n minus 1 minus 2 times lower minus higher. 3 degrees of freedom. Degrees of freedom is 3, okay. Try to solve this problem. The previous question, what is the degrees of freedom? So what's the formula for degrees of freedom? So I gave two formulas, right? So just listen here. So degrees of freedom for a kinematic chain, this is 3 into n minus 2. This is for a kinematic chain, okay? Whenever I say kinematic chain, if no links are fixed, that is called as a kinematic chain. If any links are fixed, that is a mechanism. A linkage is a mechanism, okay? Linkage is a mechanism. Mechanism in the sense, one link is fixed in it. Okay, if no links are fixed, that's a kinematic chain and you have to go for that formula. So if you look at the question, in this question, so there are 5 links, okay? There are 5 links. Degrees of freedom will be n minus 1 minus 2 times number of lower pairs. If you try to count number of turning pairs here, so link 1 and link 2 are connected by a turning pair. 2 and 3 are connected by turning pair. 3 and 4 are connected by turning pair. 4 and 5 and 5 and 1 are connected by turning pair. So basically there are 5 turning pairs, 5 lower pairs are there, no higher pairs. I can say degrees of freedom is 2. Degrees of freedom for this mechanism is 2. What does this degrees of freedom 2 mean in a mechanism? Just listen here. The mechanism is given something like this. This is the mechanism. This is the mechanism and you got degrees of freedom as 2. Whenever I say degrees of freedom is 2, if degrees of freedom is 1, it means that for a unique input, you are having a unique output. So I can say you can give only one input to the mechanism, you will get a unique output. Okay? So whenever I say degrees of freedom is 2, it means that, so whenever I give some input here, the output is not unique, okay? The output is not unique. If the output is not unique, I can say the output is not predictable, okay? Output is not predictable. There are 2 different cases happening here. When I rotate this link, so the output link may also rotate. This is one possibility. This is one possibility. So this is one expectation. And one more thing, this can also be like this. When I give motion to this link goes like this and this link comes here. but there is no motion transmitted to this link. This link didn't even move at all. Are you getting my point? So this can also happen. So I can say whenever degrees of freedom is 2, or I can say more than 1, it means that the output is not unique or the output is not predictable. If degrees of freedom is 1, the output is unique. Okay. So what should we do? This kind of mechanisms we call them as unconstrained mechanisms. Whenever you get degrees of freedom for 1 for a mechanism, we call those mechanisms as constrained mechanisms. Whenever degrees of freedom is more than 1, we call them as unconstrained mechanisms. So if you want to make these kind of mechanisms constrained in the sense, so to have a unique output in these kind of cases, what we need to do? What we need to do is, we need to increase number of inputs to number of degrees of freedom. Degrees of freedom for this mechanism is 2. I need to give 2 inputs so that I can have a unique output. So you can give the inputs anywhere. So if I give the input here and here, I can exactly predict what exactly is going to happen at the output. So by giving 2 inputs, so we can make the mechanism constrained, or we can have a unique output. Okay. So if degrees of freedom for a mechanism is 1, it is a constrained mechanism. If it's more than 1, it's called as an unconstrained mechanism. And we can make those mechanisms constrained by increasing number of inputs to number of degrees of freedom. Just write down like this. Degrees of freedom of a mechanism indicates. Degrees of freedom of a mechanism indicates. Degrees of freedom of a mechanism indicates number of inputs required. Number of inputs required to make the mechanism constrained. Number of inputs required to make the mechanism constrained. Number of inputs required to make the mechanism constrained. Degrees of freedom of a mechanism indicates. Degrees of freedom of a mechanism indicates number of inputs required. Number of inputs required to make the mechanism constrained, or to have a unique output from the mechanism. Or to have a unique output from the mechanism. Here degrees of freedom is 2, we need to give 2 inputs to the mechanism so we can have a unique output from the mechanism. Okay. Okay. That's the degrees of freedom for a mechanism. That's the significance. You understood, right? If degrees of freedom is 1, we say it's a constrained mechanism. If degrees of freedom is more than 1, it's an unconstrained mechanism. And that can be constrained by increasing number of inputs to number of degrees of freedom. Try to answer this question. So if you see the hatched region, whenever you see this kind of hatching, okay, whenever you see this kind of hatching, it is a single link, okay. This entire thing is a single link, F, D, E, this is a single link. And if you see A, B, C, this is also a hatched part. Whenever you come across this kind of hatching inside the mechanism, it's a single link, okay. So I hope you can see the hatching, okay. So whenever you see this kind of hatching, it's a single link, okay. A, B, C is a single link and F, E, D is a single link. And if you try to count out number of links, ABC is 1 link, so EFD is 1 link, 2 links, EB is 1 link, so AF is 1 link and CD is 1 link. The mechanism is slightly error in the diagram. Mechanism is something like this. This is the mechanism. This is fixed link, okay? This is fixed link. This is fixed link. This is link number 1. This entire thing is link number 2. This is link number 3, 4, and 5. These are turning pairs, okay? So there is an error in the diagram. These are turning pairs. So if you see number of links inside this mechanism, number of links are 5. Count number of lower pairs. This is 1 turning pair, 2nd turning pair, 3rd turning pair, 4, 5, and 6. Number of turning pairs are 6. Turning pairs are lower pairs. No sliding pairs, no higher pairs in the mechanism also. If you try to find out degrees of freedom for this mechanism, it's 3 into n minus 1 minus 2 times lower degrees of freedom is 0. Whenever degrees of freedom is 0, it means there is no relative motion between the links, okay? If there is no relative motion between the links, you cannot transform the motion, right? The aim of a mechanism is to transform the motion. But if degrees of freedom is 0, we cannot transform any kind of motion. There will be no relative motion between links, okay? So we call these kind of mechanisms as structures, okay? Structures. Let's write down like this. Mechanism with 0 degrees of freedom is called as structure. Mechanism with 0 degrees of freedom is called as structure. Mechanism with 0 degrees of freedom is called as structure. Mechanism with 0 degrees of freedom is called as structure. Try to find out degrees of freedom for this. Just listen here. Sometimes in mechanism you may come across this kind of arrangement. This is a fixed link, okay? Or sometimes for showing this fixed link, we can also choose this kind of arrangement. So both are same, okay? Sometimes they use this kind of arrangement. This is the link. This link is fixed with the help of these two. So I can say this is fixed link, okay? This is fixed link, link number 1. This is link number 2 and this is link number 3. This is link 1, link 2, link 3. Both are arrangements. If you try to find out degrees of freedom for this, degrees of freedom is 0, okay? Number of links are 3, number of lower pairs are 3. Degrees of freedom is 0. Degrees of freedom is 0. Number of links 3 and number of lower pairs 3. It is a structure, okay? It is a structure. It's a structure. Try to find degrees of freedom for this. Try to find degrees of freedom for this. Just listen here. Whenever you see a continuous line inside the turning pair, this entire thing is a single link, okay? This entire thing, if you say continuous line here, it's a single link. If there is no continuous line and if it is shown like this, then these two are two different links, okay? But if it is shown as continuous line, it's a single link. Solve the problem assuming it's a continuous line. So try to find out degrees of freedom for this. This is link number 1. So this entire thing is single link, link number 2. This is link number 3. This is link number 4. So if you see number of links are 4. Number of links are 4, and you try to calculate turning pairs. This is 1 turning pair, 2 turning pairs, 3 turning pairs, 4 turning pairs, 5 turning pairs. So number of turning pairs are 5. Number of lower pairs are 5. No higher pairs. Degrees of freedom is 3 into n minus 1 minus 2 times number of lower. So degrees of freedom is minus 1. Okay. If degrees of freedom is negative, it is called as superstructure. Okay. Just write down like this. If degrees of freedom is negative, it is called as superstructure. If degrees of freedom is negative, it is called as superstructure. If degrees of freedom is negative, it is called as superstructure. If degrees of freedom is negative, it is called as superstructure. There is no difference between structure and superstructure. In both the cases, there will be no relative motion, okay? In both the cases, in structure, there will be no relative motion between links, and in superstructure also, there will be no relative motion between links. So, there will be no relative motion, okay? So, both these structures and superstructures are used only for transmitting forces, okay? But superstructure, it is more stronger when compared with structure, okay? That's why it's called as superstructure. It's more stronger and stable in comparison with the earlier case. Okay, both are same. There is no relative motion between both the cases. Okay. Next, write down like this. Types of joints. Types of joints. Sometimes in the mechanism there will be binary, quaternary, ternary joints. Even if we, so if I remove link 4, it's called as a structure, Gaurav. Even if I remove link 4, there will be no relative motion, okay? That's why you are getting degrees of freedom as negative. Even if you remove some links, after removing some links also, there will be no relative motion. Whenever you come across this kind of situation, you calculate degrees of freedom and you will find it to be negative. Okay? So even after removing some links, you will not have relative motion. Then it's a superstructure, okay? So I need to count just number of links, okay? Why you want to take hinge as a link? What is hinge? So these are two links. I want to connect the two links. So the joint, how I connected the two links, that is the hinge, okay? Hinge is not a link. Two links are connected, and how they are connected, it's a hinge connection. Just take down this, types of joints. Types of joints. If two links are connected at a, whenever I say joint, the point where the links are connected, okay? If two links are connected at a point, so this is called as a binary joint, okay? It's called as a binary joint. It's called as a binary joint. So in a binary joint, you'll be having 1 degree of freedom. I can say only the link moves with respect to another link. Link 2 is moving with respect to link 1. Or I can say the number of parameters required to describe motion is, the relative motion is, only one parameter is required. One parameter is required, okay? So one binary joint is one lower pair. Only lower pair has 1 degree of freedom, right? Only one independent parameter is required. So if I go for a ternary joint in the sense, it's a point where the links are connected, okay? This is a ternary joint because at this joint, 3 links are connected. 1, 2, 3. So if I want to describe position of link 3, I need to know this angle. So theta 3. So I need to know this angle. I need to know these two angles. If I just mention these two angles, I can find out the position of link 1 and link 3, or link 3 with respect to link 1, link 2 with respect to link 1, or link 3 with respect to link 2. You can get anything. So if I know these two angles, it's not required to know this angle, okay? So theta 3 minus theta 2 is this angle. Okay? So here only one parameter is required, 1 degree of freedom. So it's called as one binary joint is one lower pair. So here I can say I need 2 parameters. This is called as ternary joint. Ternary joint. This is called as ternary joint. And one ternary joint is equivalent to 2 binary joints, as I need 2 parameters for describing the motion. So our one ternary joint is 2 lower pairs. If 4 links are connected at a point, I need 3 parameters for describing position of every other link with respect to any link. So I need 3 angles. So this is called as quaternary joint. Quaternary joint. And one quaternary joint is equivalent to, so I need 3 parameters, so I can say it's 3 binary joints. And each binary joint is a lower pair, so I can say it is equivalent to 3 lower pairs. So whenever a mechanism is given in the question, please be careful with the types of joints, okay? If only 2 links are connected at a point, it's only 1 lower pair. If 3 links are connected at a point, there will be 2 lower pairs. So I can say basically 3 can be moved with respect to 1 and 2 can also be moved with respect to 1. So 1 and 2 will form 1 pair and 1 and 3 will form 1 pair. I didn't get your question. Hinge is a joint, okay? It's not a link. How the links are connected, the joint, what type of joint it is. Hinge is not a link, okay? You are already counting, this is link number 1 and this is link number 1. This link number 2. So these are 2 links, okay? So basically what is turning pair? So turning pair is something like this. These are the 2 links. So this entire thing is perpendicular to the board. So I can say this is one link and this is another link. These 2 are connected with a rivet here. Or kind of hinge or something like this. I'm not getting your question. This one. This entire thing is a single link, okay? So basically what we are doing is we are fixing this link. So instead of saying I am fixing like this, I can also say like this, right? I just say I fix like this. When I say this is a fixed link. This is link 1, link 1. This is also fixed, this is also link 1. This is also link 1. There is no relative motion between these 2, the same link. Is there any relative motion between? This is also not moving, right? There's no relative mode. It's a single link, okay. Either you can show the fixed link like that or like this. Anyways. Basically, I want to fix this. How you fix this? I can just set the area like this or like this. Please be careful with the types of joints, okay? Sometimes two links may be connected at a point, it's a single lower pair, one turning pair. If three links are connected, there are two lower pairs here. If four links are connected, there are three lower pairs. It's not two bearings. It's not two bearings, mister. I can say how many independent motions we can have. How many independent motions we can have? I can say like this. Here I can move link 2 with respect to link 1. Only one related motion. Here, if I take link 1, I can move 3 with respect to 1. I can move 2 also with respect to 1. Two related motions. Here I can move 2 with respect to 1, 3 with respect to 1, and 4 with respect to 1. 4 independent motions, I can say. We have to just count how many parameters required to disturb the motion, how many independent motions we are having. Try to calculate degrees of freedom for this. So it is a slider, okay? It is a slider, it's a mistake in the diagram. This is a turning pair, okay? This is a turning pair. And this is a slider, okay? Please make a small correction with the diagram. It's something like this. This arrangement is like this. This is a slider, okay? This is a slider. So whenever you see a continuous line in the hinge, it's counted as single link, okay? It's a continuous line, okay? So with this mechanism, which option is correct? Is it a structure or it's a mechanism with 1 degree of freedom or mechanism with 2 degrees of freedom? Mechanism with more than 2 degrees of freedom. So which option is correct? Option D. Let's try to count number of links. So this is fixed link, link number 1. Fixed link, link number 1. This is slider is link number 2. This slider is link number 2. And this entire thing is link number 3. And this entire thing is link number 4. It's a single link, okay? It's a continuous line. Single link. So this is a single link, link number 5. This is single link, link number 6. This is single link, link number 7. This is single link, link number 8. Link number 9 and link number 10. If you see number of links in this mechanism, number of links are 10. Try to count number of turning pairs or number of lower pairs. 1 turning pair, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 turning pairs are there, okay? Total 12 turning pairs are there. And you can see 1 and 2 are forming a sliding pair, okay? This is a sliding pair, okay? This is a sliding pair. 2 and 3 are connected by turning pair, but 1 and 2 are connected by sliding pair. Plus 1 sliding pair. 12 turning pairs, 1 sliding pair. Total 13 lower pairs are there. And there is no higher pair. Higher pair is point or line contact. There is no such pair here. Calculate degrees of freedom for this. It's a mechanism, okay? Degrees of freedom is 3 into n minus 1 minus 2 times number of lower pairs minus higher pairs. Degrees of freedom for this mechanism is 1. Only one possibility is that you can push inside and close outside. It's your the gate mechanism. Option C. So the given figure shows it's a kinematic chain, okay? It's a kinematic chain because no link is fixed. It's a kinematic chain since no link is fixed. Calculate degrees of freedom for this kinematic chain. So for a kinematic chain, degrees of freedom is 3 into n minus 2 times lower minus higher. So try to calculate number of links in that. Number of links are 5 and there are 5 lower pairs, 5 turning pairs, no higher pairs. So degrees of freedom for this kinematic chain is 5, okay? For a kinematic chain, if degrees of freedom is 5, it's an unconstrained kinematic chain, okay? Or in other ways, I can say to answer this question, you can make this as a mechanism. If you make it as a mechanism, you find how many degrees of freedom this mechanism will have. If I make it as a mechanism, So in a mechanism, one link is fixed, okay? So degrees of freedom for a mechanism. In a mechanism, one link is fixed. So I can say when you fix one link, that link will lose all the 3 degrees of freedom. It cannot move in x direction, y direction, and it can rotate about z axis. So if I make this as a mechanism, degrees of freedom will be 2. A mechanism with more than 1 degree of freedom is unconstrained mechanism, and a kinematic chain is unconstrained kinematic chain. Okay. So what is the minimum number of degrees of freedom for any kinematic chain? What is the minimum number of degrees of freedom for any kinematic chain? 3, okay. So for a kinematic chain, minimum we will be having 3 degrees of freedom, okay. So if I make this as a kinematic chain, this is a locked chain, okay. So minimum you will be having 3 degrees of freedom. What are the 3 degrees of freedom? I can move this in an entire chain in x direction. I can move the entire chain in y direction. I can rotate the chain about z axis. For any kinematic chain, you will be having minimum 3 degrees of freedom. So the entire kinematic chain can be moved in x, y, and it can be rotated about z axis. Apart from those 3, in the given mechanism, apart from those 3, inside the mechanism, you can have 2 independent types of relative motions. So total 5 degrees of freedom, okay? So 3 plus 2, basically it's 3 plus 2. For the whole chain, we'll have 3 degrees of freedom. And inside that kinematic chain, the given question, so there will be 2 more relative motions, independent relative motions, which we have discussed, okay? For the mechanism, in this case, when we fixed a link, 2 possible cases. Those are the 2 possible relative motions, okay? Let's try to answer these questions. Solve the problems assuming it's a mechanism, okay? All our mechanism, in first question, link 1 is fixed, okay? It's not fixed here, but you solve the problem assuming link 1 is fixed. So find the degrees of freedom of following mechanisms, okay? All our mechanisms here. So fix link 1 and solve the problem, okay? If link 1 is not fixed, it is a kinematic chain, okay? So please be careful with the types of joints, okay? Binary joint, ternary joint, and quaternary joint. What's the answer for the first question? Let's look at this first one. So in the first case, number of links are given as 8. So try to find out number of lower pairs. So while calculating number of lower pairs, be careful with the types of joints, okay? Are there any ternary joints in first question? Are there any ternary joints in first question? There are 2 ternary joints, okay? So if you look at this link, if you take any hints like here, 7 and 1, only 2 links are connected. 1 and 2, only 2 links are connected. This is link number 4. So 1, 2, and this is 3, this is 4, this is 5. This is 6, okay? 6 is missing. This is link number 6, this shaded part. 6 and 1 are connected here. So 8 and 6 are connected here, only 2 links. 8 and 3, if you take every joint, at all the joints only 2 links are connected, okay? At all the joints only 2 links are connected. If you look at this joint in the top left, 7 and this is, I'm calling this as 4, 7, 4, these 3 links are connected, okay, here. 3 links are connected here at this point. It's a ternary joint, there are 2 lower pairs here. And this is also a ternary joint, you can see this link and this link and this link. 3 links are connected here. This is also a ternary joint. So here also 2 lower pairs are there. One ternary joint is 2 lower pairs or 2 binary joints. Here I have 2 lower pairs, here I have 2 lower pairs, total 4 lower pairs. 4, and this is 5, 6, 7, 8, 9, 10, and this is 11. Total 11 number of lower pairs are there. Total 11 number of lower pairs are there. In this question there are 2 joints, okay, two binary joints. Two binary joints. So you can see the link number 647. 647, 3 links are connected, it's a ternary joint. 635 are connected, it's a ternary joint. Okay, these two are ternary joints, and those two ternary joints, there are 4 lower pairs. Apart from 4, 5, 6, 7, 8, 9, 10, 11, total 11 lower pairs are there. No higher pairs. If you try to calculate degrees of freedom, I am solving the problem assuming link 1 is fixed, okay. So then it will be 3 into n minus 1 minus 2 times lower minus higher. 3 into n minus 1, so minus 2 times number of lower pairs. So I can say degrees of freedom is minus 1, okay. Degrees of freedom is minus 1. Degrees of freedom is minus 1. It's a superstructure, okay, first case. And in the second case, if you see number of links are 8. Number of links are 8. And if you see this joints, all the joints are binary joints, okay. All the joints are binary joints. Count the number of lower pairs. So 3 lower pairs here at the bottom. So 3 lower pairs, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 number of lower pairs are there. So no higher pairs. So degrees of freedom will be 3 into n minus 1 minus 2 times number of lower pairs. No higher pairs. Degrees of freedom is 1. For the second case, degrees of freedom is 1. And for the third case, if you see number of links are 11. So if you see the ternary joints, you can see this joint 9, 11 and 5. This joint 9, 11 and 5, this is a ternary joint. Here I have 2 lower pairs. And one more joint, this is also a ternary joint, 7, 8 and 2. So here also 3 links are connected, it's a ternary joint. So here I have 2 lower pairs, here I have 2 lower pairs. Total 4 lower pairs. Apart from these two, everywhere it's a single lower pair. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 plus 2, 12 plus 2 is 14. So total number of lower pairs are 14. No higher pairs here. If you try to find out degrees of freedom, it is 3 into n minus 1 minus 2 times number of lower pairs. Degrees of freedom is 2. So number of lower pairs in the last case are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, there are 15 lower pairs. The last case, there are 15 lower pairs. So degrees of freedom is 0, okay. Yeah, so there are 15 lower pairs, you count them. So 2 ternary joints and all other are binary joints. I forgot to count 4 and 8, okay. 4, 8 are connected by a binary joint. I forgot to count that 4, 8 turning pair. Yeah. So you understood this, right? So whenever a mechanism is given, try to identify these joints, okay. Binary joints, ternary joints and quaternary joints. Three. So number of links are, this is fixed link, okay, link number 1, link number 1, link number 1. So this is link number 2, this is link number 3, this is link number 4, this is link number 5, this is link number 6, this is 1, this is 7, this is 8, this is 9, and here it is 10. Number of links are 10, okay. Number of links are 10. Try to count number of lower pairs. Number of lower pairs, it's 1 turning pair, 2 turning pairs, 2 turning pairs. Here it's not connected, you should not count, okay. If it's connected, then only you have to count it. So it's not connected. 1, 2, so this is 3, 3, 4, 5, 6, 7, 8. So 8 are binary joints. 8 are binary joints. 8 are binary joints. If you look here, 3 links are connected, 7, 9 and 8. So here I have 2 lower pairs. Here I have 2 lower pairs. And here you can see here, how many links are connected? This is link number 5 and this is link number 7 and the slider is link number 6. 3 links are connected here. So here also I have 2 lower pairs and one more sliding pair, okay? One sliding pair. One sliding pair. So 8 binary joints plus 2 ternary joints plus 1 sliding pair. So this is 8, 8. So 2 ternary joints in the sense 4 lower pairs plus 1. So how many number of lower pairs? So 13 number of lower pairs are there, no higher pairs. So try to find out degrees of freedom. 3 into n minus 1 minus 2 times lower. Degrees of freedom is 1. 12 lower pairs. So maybe you have not counted this sliding pair, I think. You have not counted the sliding pair. Just listen here. Number of lower pairs. 1 turning pair. This is a binary joint. This is a binary joint. 2, 3, 4, 5 binary joints. 5 binary joints. 6, 7 binary joints. 8 binary joints. Okay? You agree with this? 8 binary joints are there. 8 binary joints in the sense 8 lower pairs. Plus, here 3 links are connected, 7, 9 and 8. So this is a ternary joint, okay? This is a ternary joint. Here again 5, 7, 6. It's also a ternary joint. Plus 2 ternary joints are there. 2 ternary joints in the sense each ternary joint is 2 lower pairs. 2 ternary joints in the sense 4 lower pairs are there. So apart from this, so this is a sliding pair. 1 sliding pair. Sliding pair is also lower pair. So be careful with the types of joints, okay? That's very important. But till now there are no questions in GATE based on this. Let's try to solve this problem. Let's try to listen this. So I'm fixing a nail on the board. I'm fixing a nail on the board. So I just fixed a nail something like this. So I fixed a nail on the board. On this nail what I'm doing is I'm keeping one disc. I'm keeping a disc on this nail so I can spin the disc about this nail. I can spin the disc about this nail. I can spin the disc about this nail. I can spin the disc about the nail. Nail is fixed and the disc is spinning. And on the same nail what I'm doing is I'm keeping an arm like this. So this arm is having a projection into the board, I can say. On that projection I'm keeping one more disc. So I kept this on the projection, okay. The arm is having a projection, something like this. On the projection, I place the second disc. And the second disc and this are having a point contact. So basically, I can say this arm is fixed, right? This is a kind of an epicyclic gear, okay? It's an epicyclic gear. So I just told it's a pin, but it's not pin, it's bearing, okay? It's a bearing. So this is the arm of an epicyclic gear. And this is the mating gear. Try to find out degrees of freedom for this system. This was a recent GATE question, okay? I hope you understood the problem, right? So first I took a nail. On the nail I placed the disc. And on the same nail I placed this arm. Okay? Just listen here. So I told that I fixed a nail here on the board. So this nail is link number 1, it's a fixed link, okay? This is fixed link. On this nail I placed this disc. This is link number 2. This disc can rotate about this nail. It's a different link, link number 2. On the same nail I placed an arm here. So this is link number 3. Arm is link number 3, okay? Arm is link number 3. On the arm, so I have a projection. And on that projection I placed this disc. So the 2 discs are in contact. So this link is link number 4, this disc is link number 4. If you look at this point, so first I took link number 1, that is the nail. Nail is link number 1. And on link number 1 I placed the disc, that is link number 2. On the same nail I placed link number 3. So at this point if you see link 1, that is the nail, that is the board. Link 2 is the disc, link 3 is the arm. 3 links are connected. So board is fixed link, this is link number 2 and this is link number 3. 3 links are connected at this point. I can say this is a ternary joint, okay? This is a ternary joint. I have 2 lower pairs here. This is link number 4 and this arm is link number 3. 3 and 4 are connected by turning pair here. This is 1 lower pair. And you can see these 2 are connected by a point contact. This is a higher pair. if you try to find out degrees of freedom for this mechanism, so this is fixed link, okay, the nail is nothing but the fixed part. So degrees of freedom is 3 into n minus 1, number of links are 4, so 4 minus 1, minus 2 times number of lower pairs. Here I have 2 lower pairs and here I have 3 lower pairs. Number of higher pairs, there is 1 higher pair in the mechanism. So I can say degrees of freedom is 2. For an epicyclic gear, the degrees of freedom is 2. And what are the 2 degrees of freedom? When I rotate this gear, the other gear rotates. That's 1 degrees of freedom. And apart from that, you can rotate axis of this gear about axis of another gear. So those are the 2 degrees of freedom. So what is this nail? Just listen here, I fixed a nail on the board. On the nail, this disc is rotating, okay? This disc is rotating on this nail. So I call this nail is nothing but the fixed link, right? Board. This is link number 1 and this is link number 2. 2 links. And on the same nail, I mounted this arm. This arm can rotate about this nail. So this is link number 3. 3 links are connected at this point. Any doubts on this? So nail is different and the link is different, okay? Nail is fixed on the board, whereas this disc can rotate on that nail. Any doubts in this? You understood this? So basically I fixed the nail. So nail fixed in the sense that the board is link number 1, okay? On the board you are mounting this disc. You can rotate this disc. Okay, this is all about degrees of freedom. There are certain cases where this Kutzback's criterion fails, okay? If you look at the Kutzback's criterion formula, so Kutzback's criterion formula, if you see, so Kutzback's criterion formula is 3 into n minus 1 minus 2 times number of lower pairs and number of higher pairs. This is Kutzback's criterion for degrees of freedom. So for calculating degrees of freedom, Kutzback's just considered number of links, number of lower pairs and number of higher pairs, but he didn't consider the geometry of links, okay? So because he didn't consider the geometry of links for calculating degrees of freedom, so this empirical relation will not give correct result all the time, okay? So there are few cases where this relation will give incorrect results.